In this problem, we're measuring virtual social influence using the clout measure. We're going to look at the number of tags received last month by a random sample of 80 individuals. So the first couple of parts here are some review. The element in this problem, under part A, I, the element is one individual website. And the variable will be the number of tags received last month. And the sample is a simple random sample of 80 individual, it's really individual websites. And the population then would be all of the individual websites. If you had, on this problem, just put on the element one website, and then in 3 put 80 websites, and 4 all websites, that would have been sufficient to answer this question. So on part B, also a little bit of review. Suppose we want to know if the population mean number of tags was less than 75, B, part I. That's just writing a research hypothesis, which is mu, that's the population parameter for when we're looking at means, less than 75. And then for part I, or 2 for part B, the statistic you would calculate to test that hypothesis would be the sample mean. So again, as we've stated before, you calculate the sample statistic, in this case x bar, from the sample, and you use that in order to estimate or test some hypothesis about the population mean. Okay, if you need to hit pause, go ahead. I'm going to, as quickly as I can here, move down the page. Okay, so here are the actual values from the problem. And the first thing it asked you to do was a stem and leaf display. And so since we have numbers, okay, so we're on a stem and leaf display, which, since I have the numbers in order, that's not going to be very hard to do. But we'll do it anyway, just to get the idea of it. Since our numbers are going from 0 to 136, I'm going to use stems that would be designate the tens place. So 0, 1, 2, 3, 4, and we'll go on down to 13 here. And then I'm going to have my leaves over here. And so for the first 5 numbers, that's 0. And then follow that with 3, 4, 4, 6, 7, and then 3 nines. And then in the tens, we're going to start with 12, 14, 18, 19. Into the 20s, 0, 3, 4, 4, 5, 5, 7, 7, 8, and then 29. In the 30s, 1, 2, 3, that's it. I didn't even need that last column. On the 4s, 3, 3, and 6. And the 50s, I've got 52, 56, 56. That's a 6 there. And another 6, and then an 8. And the 60s, pair of zeros, a 1, a 4, a 5, and a 6. And then in the 70s, just one number. And the 80s, 2, 3, 7, and 8. Then in the 90s, 2, 4, 8. Then in the 100s, before we get to 110, 101, 101, 103. Then nothing in the 110s. In the 120s, 7 and 8. Then in the 130s, 2, 6, and 6. And so there's your stem and leaf display. Just looking at this, it looks like there are quite a few people at the lower end, and then kind of maybe a little bit of a skew going to, if you turn this over and looked at it as a histogram, this would be skewed to the right. In fact, one way of looking at the stem and leaf display, just to make bars just like you would have on a histogram. And of course, later on we will wonder whether or not some of those higher values are outliers or extreme values. Could be. We'll figure it out. Again, if you turn your head sideways, that's going to look like a histogram, and maybe a little bit of skew down to the right. Here. So the next thing we're going to do is the 5-number summary, which is just the minimum value, the first quartile, the median, the third quartile, and the maximum. So the minimum value, of course, is 0, and the maximum is 136. And let me tell you that, especially if I have you do something by hand, I'll always just put the numbers like this. I'll have 4 columns of numbers and the same number of numbers in each one. If you have something more complicated than this, you should use a calculator or a computer. So anyway, 1/4 of the values are down here. And so what we need is a value between 14 and 18 that will be the first quartile. In other words, 25% of the numbers, or 1/4 of the numbers, will be below that point, and 75% or 3/4 above that point. And what we'll do, and what most computer packages and certainly the TI calculators will do, it'll just split the difference between the 14 and 18. So we'll have 16 there. I guess technically any number between 14 and 18 really is a first quartile, because if I had the number 15 or the number 17, all of those fit the definition of 1/4 values below and 3/4 above. Anyway, the most common thing is just to split the difference. Occasionally you'll find something that with this quartile, what they'll do is, since it's a quartile, they'll go 1/4 of the way from 14 to 18. In this case, that would be 15. But we'll stick with the 50%, or just split the difference. So we'll do the same thing now with the median. 33 and 43. So we'll need some value between those to serve as the median. And we'll just go halfway between those, and that is 38. And then for the third quartile, we will go between 70 and 82, so I believe that'll be 76. And so that is the 5-number summary, just the 5-number summary of some important positional numbers: the minimum, the first quartile, the median, third quartile, and the maximum value. And then a simple box plot is just a graph of those numbers, and I will put that up here. And so I'll just put an axis here of 0, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120, 130, 140, 150, 60, 70, 80, 90, 100, 110, 120, 130, 140, 150, 60, 70, 80, 90, 100, 110, 120, 130, 140, 150, 60, 70, 80, 90, 100, 110, 120, 130, 140, 150, 60, 70, 80, 90, 100, 110, 120, 130, 140, 150, 60, 70, 80, 90, 100, 110, 120, 130, 140, 150, 60, 70, 80, 90, 100, 110, 120, 130, 140, 150, 60, 70, 80, 90, 100, 110, 120, 130, 140, 150, 60, 70, 80, 90, 100, 110, 120, 130, 140, 150, 60, 70, 80, 90, 100, 110, 120, 130, 140, 150, 60, 70, 80, 90, 100, 110, 120, 130, 140, 1 120 and 130. So I should have drawn that down a little bit here. Okay, so the box of the box plot extends from Q1 to Q3, or from 16, call that 16, up to 76, somewhere around here. And then a line in the middle for the median, 38, and then extend whiskers down to the low value and up to the highest value, which is 136. So that is a simple box plot. So if we wanted a box plot that would designate outliers and extreme values, what we would need to do is first compute the interquartile range. For outliers, we would go 1.5 IQRs from the box, and for the extreme values, 3 IQRs for the box. What I'm going to do now is I'm going to change one of the numbers, because I can tell, IQR is the width of the box, that there aren't going to be any outliers or extreme values in this problem, because if I went the width of the box on the bottom, I would be down here somewhere for the 1.5, and then on the top, it looks to me like we haven't even gotten, with our highest value, maybe about 1 IQR above, and we need to get 1.5 above for there to be an extreme value. So what I'm going to do is I'm going to change this 136 number. I'm going to change that to 336. And this is going to be a little tough to show. And let me do two things here. I'm going to have a 136 and a maybe 206. We'll see how that works out. Okay, what I'm going to do in this case, just because my graph is kind of extended out there, I'm going to change the scale of the graph and redraw it down here. So if you have enough room on your paper, you wouldn't have to do this, but anyway, I'm going to go 0, 20, 40. Maybe I shouldn't even do it that much. Let me see if I can. Okay, can you help me out with the eraser here?
Just pick it up. Oh, I'm sorry. You would select. No, not that one. You would do. Yeah, just go ahead and use your pen. You've got it selected now.
Oh, okay. All right. Yeah. The pen instead of the eraser.
Right.
Okay.
Because, yeah, we're using the integrity tools instead of.
Okay. Good. So anyway, now let's see if I can do this over here. This works a lot better with you in the room. Amazing. That's how technology works. When you have problems and you've got the technology person here, the problems disappear automatically. Okay, so anyway, I'm going to go 0, let's say 50, 100, 150, 200, 300, and 350. Okay, so in order to, I guess I'm going to start here. I'm just going to redraw the box just like it was. Remember, the box went from 16 to 76. And I know we're not going to have any outliers or extreme values on the bottom, so I'm just going to extend down to the lowest value, down to 0 again. And the median was 38. That's about right here. And so now I'm going to try and figure out where there might be some outliers. Erase some of this up here. And back here. Okay, so to get an outlier is in the interval of the box plus or minus 1.5 interquartile ranges. Okay, I lost a little bit of ink there, so if you need to, I'm going to repeat a little bit of stuff here. So if you need to, then you can maybe skip ahead on your video a little bit. Anyway, coming back here, make sure I have that set up. I'm going to read just without any explanation, just put the summary here. And remember, I had changed these two numbers to, I think, 336 and maybe, I think I did 206, but we're doing 206 now, that's for sure. So anyway, the maximum now is 336. And I wanted to do my box plot, but this time I wanted to add outliers and extreme values. So I'm going to make a new axis here. And then I'm going to put the box just where it was before, starting at 16, the Q1, and going up to 76, Q3. Put a line in the middle for the, or wherever appropriate, for the median at 38. I know there aren't going to be any outliers or extreme values in the bottom, so I'm just going to extend down to 0. Now what we want to do is check to see if there are any outliers or extreme values. And I'm going to check for outliers first. An outlier is anything that is more than 1.5 IQRs from the box. So we're going to get the IQR first. I'm going to just do that over here. IQR is just the width of the box, which is just Q3 minus Q1. So that'll be 76 minus 16, which is 60. And so to go from the box, if I were going on the lower hand side, I would do Q1 minus 1.5 IQRs. But since there aren't any down there, I'm not going to do that on this one. So on the top, I'm going to go Q3. Again, I'm going from the edge of the box. On the lower, I'll repeat that. I would have gone down. But I'm going to start at Q3, and I'm going to add 1.5 interquartile ranges. And so that's going to be 76 plus 1.5 times 60. And that'll be 166. And so any value beyond 166, I'm going to write down here, anything above there is at least an outlier. So now I'm going to check to see if there are any extreme values. And for extreme values, we're going to do the box plus or minus 3 IQR, 3 interquartile ranges. And so 76, since we're on the upper hand side, plus, since we're going above the box, and that's going to be 3 times 60. And for extreme values, we go 3 IQRs away. So what'll that be? 180. I think that's 2 256. Is that right? Let's see, 180, yes, 256. So anything above 256 is going to be an extreme value. I'm going to go ahead and rewrite over here that this was 166. So I'm going to look at, is there anything greater than 256? Yes, 336. So that's an extreme value, and I'm just going to draw an asterisk there. There are no other extreme values. So 206 is over here, right here. It's above 166, so at 206 I'm going to have an outlier. And then I'm going to take the, in this case if it was on the lower side it would be the lowest, but the highest value, the 132, that's neither an outlier nor an extreme value, and I'm going to extend the line up to 132. The last value that's neither an extreme value nor an outlier. That's okay. Okay, so next thing we want to do is a frequency distribution or a set of frequency distributions. I think I'll do those up here. First of all, let me tell you, just to keep this a little bit simpler and take up less room, I'm going to go back and leave these numbers at 136 instead of what I used just a minute ago to illustrate outliers and extreme values on the box plot. So the other thing I'm going to do is I'm going to call the first class, what was this? And this was number of tags. I'm going to say greater than or equal to 0, but less than 20, greater than or equal to 20, but less than 40, 40, but less than 60. Please make sure that you define the classes clearly, and there's no question about where any kind of value, whether it had decimals or not, where it would fit in your distribution. So don't, for example, just say 100 to 119, 100 but less than 120. By the way, it's, I think generally better to stay on the first side greater than or equal to 100, because when you think of numbers starting at 100, if you just said greater than 100 there, then 100 itself wouldn't be in this class. That would be a little odd, I think. So for the frequency distribution itself, we're just going to count how many are in each category. So in the first category, 0 but less than 20, we have 17 values. Then greater than or equal to 20 but less than 40, 13 values. Greater than or equal to 40 but less than 60, 8 of those. 60 but less than 80, 7 of those. 80 but less than 100, 7 of those. 100 but less than 120, 3 of those, and then 5 here. That does add to 60, which was the number of numbers that we had in the data set. So relative frequency, same thing as proportion in each class. We're going to have 17 out of the 60. And that's about 283, but I'm just going to carry it 2 places for right now. Then 13 divided by 60. That's about 0.22. That's 0.22. Then 8 divided by 60, 0.13. 7 divided by 60, about 0.12. I don't know why it's, let me see if I can get that a little neater. There's the same thing here. Then 3 divided by 60, 0.05. Now what I'm doing, I just need to... Hi. Then 5 divided by 60. That's 0.083. Get that to be 0.08. And that does add to 1, which it should. So now we have the frequencies and the relative frequencies. I'm going to finish this part. If I don't, I'll lose all of this. So I've got the frequencies and the relative frequencies. Now I'm going to get the cumulative frequencies, which I'm going to start with, I'm going to go less than 0 would have 0 in it, and then less than 20, these then become, and this one, the cumulative things, less than 20, I have 17 values. And then less than 40, those 17 and another 13 or 30. Then those 30 plus another 8, we've got 38. Plus another 7 is 45. Then another 7, that's 52. Then 3, that's 55. And then 60. And of course, you should end up with 60. The total number of values in the data set less than 140 is close to the whole data set, and that is 60. Then we can have the cumulative relative frequency. So now I'm starting at the 0.28. So first of all, less than 0, again, is 0. Then 0.28. Let me change the color of this. 0.28, getting the things in this column, plus 0.22 will be 0.5, plus 0.13 is 0.63, plus 0.12 is 0.75, plus 0.12 is 0.87, plus 0.05 is 0.92, plus 0.08 is 1. And so these are just proportions, so the proportion of values less than 140 is 1. So now you can use this, any of these distributions to answer questions about the number or proportion of values in each category, or the number or proportion of values below a certain point. So if I want to know, just looking at this, if I had this, what number of values were less than 80, I would just come over to cumulative frequency, and that's 45. If I want to know the proportion of numbers less than 60, then I need cumulative relative frequency, so I'd be here. If I want to know the number of numbers below 120, less than 120, less than, if I want to know the number of numbers in the class 120 but less than 140, I'd have here. So you can answer a variety of questions. The one I left out here, the proportion of numbers in the class 40 but less than 60 here. So I've got frequencies, the number in each category, relative frequencies, the proportion in each category, cumulative frequencies, the number of numbers below each point here. So I'm just looking at starting at less than the lower limit and then less than each of the other numbers that are there. Cumulative relative frequency uses those same classes, less than 0, less than 20, less than 40, and so on, but gives you the proportion or the relative frequency as we go down the list into each category. Now I'm going to make a graph of this frequency distribution would be a histogram. And so all I'm going to do over here is make me a chart here. And on the x-axis, I'm going to go 0, 20, 40. So a histogram is going to look like a bar chart, but it's not quite a bar chart. A bar chart is used for qualitative variables like the number in the category red, the number in the category green, and so on. This axis has a numerical meaning, in this case the number of tags. So in the first class, 0 to 20, there were 17 values. Let me do this first, get the axis here. This is going to be 5, 10, 15, and 20. So in the first class, I had a frequency, which is what these are, frequencies of 17. So that's about that. In the next category, 13, about like that. The next category, 8. The next category, 7, and the next category, okay, somewhere here I've got, let's see, I had 17, 13, 8, aha, that should have been 100, let me skip along there, 100, 120, and then 140. And so in 80 to 100 we had 7 again, then 3, then 5. And so that is just a frequency histogram. Sometimes you'll see the need for a relative frequency histogram. And so we just want to get the relative number in each category. I'm just going to work right off of what we have here and add an axis that says relative frequency distribution, relative frequencies. So 5 divided by 60 was 0.08. Then we'll have 0.16, 0.24. It's 0.32 at the top there. And so now I can just read relative frequencies across. The real advantage of a relative frequency histogram, I guess it does have in its own right, you can read the proportion in each category across, but the real advantage of that comes when you're comparing two separate distributions if you have that are of different, maybe especially wildly different sample sizes. So if you look at one histogram based on a sample of 100, you might get something that looks like that. If you had another one that was out of, let's say, 500, it's just going to be a lot taller just because the sample size is large and a little bit harder to compare those. That's if you had just frequency distributions. If you had relative frequency distributions, then they're both going to be on the same scale, and it's a little bit easier, well, a lot easier to make comparisons between the two groups. Okay, so moving on to a problem we're going to compute means, standard deviations, covariance, and correlation. before I compute, I just want to address some of the questions though that do not require any computation. So, for example, on give me a second here. On Part D, it says we're going to compute the means for each variable. Of course, that means we're going to compute x bar and y bar. We have variables here of x and y, so we're just going to compute the mean of each one. You've already covered that already, but we'll recompute that here. On Part E, it asks you to write the symbols for the population parameters estimated in the preceding problem. We're going to get the mean of the x's and the mean of the y's. Mean of the x's, mean of the y's. So we're going to compute the sample mean of the x's to estimate the population mean of the x's and the sample mean of the y's. Let me make that come out a little bit clearer here. Maybe. Maybe not. I'll rewrite that there. It's y bar. So x bar and y bar. Anyway, we compute the sample mean y bar in order to estimate the population mean of the y's. So then we're going to compute the two standard deviations. So for Part F, we're going to compute the standard deviation of the x's and the standard deviation of the y's. Then in Part G, it says to write the symbol for the population parameters. That'll be the population standard deviation of the x's and the population standard deviation of the y's. So we're going to compute the sample covariance. That's just, I'll write it over here, COV for x and y, and the symbol for the parameter on that one is just large COV XY. So lowercase for the statistic and uppercase for the parameter. Although I have to admit we won't talk about estimating covariances too much, so I'm a little less concerned with the distinction between those symbols, as long as you have COV XY and understand that that is a covariance. It does become important in more advanced statistics, but for our purposes, covariance is primarily something we use as an intermediary number to get to sample correlation. And so in Part J, we're going to compute R, the sample correlation, and then the parameter for that, Part K, is rho. So at least in terms of the symbols, the x bars and the mu's, maybe we've added a little bit more by putting a subscript by them, but should be familiar with most of these symbols already, except for the only one new really tonight is the covariance. Okay. Just want to get this all on a separate page here so we have as much space as we can. Okay, so there are values of x and y. And so the first thing we're going to do is compute the sample mean and the sample standard deviation. The sample means for each variable. Then we'll get to the standard deviations. But I'm going to sum the x's, and I get that to be 30. And sum the y's, and I get that to be 20. So x bar, the sample mean, is equal to the sum of the x's divided by n, and that's 30 divided by 5 is equal to 6. And the sample mean for the y's, the y bar, is that well, I thought I had that a little while earlier. Okay, well, that was kind of ugly. That's what I get for messing around with it. Well, let me give this another try here and see how it works out. Let me write this over here. X bar is equal to the sum of the x's divided by n, and that's equal to 30 divided by 5, which is 6. The mean of the y's is equal to the sum of the y's divided by n, which is 20 divided by 5, which is 4. So there are the sample means. We want to compute next the sample standard deviations. So before we can do that, I'm going to go ahead and write the formulas down here. So the standard deviation for the x's is going to equal the square root of the sum of the squared deviations. That's a minus sign there. The sum of the x sub I minus x bar squared divided by n minus 1. And for the y's, sy is equal to the square root of the sum of the y sub I minus y bar squared divided by n minus 1. So, coming up to my calculation table here, I had x sub I and y sub I. So I'm going to take each x and subtract the sample mean. So I'm subtracting 6 from each one of these. I get minus 3, 1, minus 4, 2, and 4. And checking here, that does add to 0. Good. I'm going to go ahead and get the y deviations right now, subtracting 4 from each value. So I've got y sub I minus y bar. So I'm subtracting 4 from each one of these. Minus 3, 0, minus 3, 1, and 5. Of course, that sums to 0. Then I'm going to square each of those. And I'm going to change the color here. I'll tell you why in a minute. I'm going to get x sub I minus x bar squared, 9, 1, 16, 4, and 16. And I'm going to sum those up, and I have 46. And I'm going to get y sub I minus y bar squared, 9, 0, that was a 0 right there, 9, 1, and 25. And when I sum those, I get 44. So now for my standard deviation for the x's, I've got this sum right here of 46, the square root of 46 divided by 4. There were 5 numbers here, so n minus 1 is 4. And that comes out to be 3.39. So for the standard deviation for the y's, the square root of, and now I have the sum of squared deviations right here. That's 44, again divided by 4. And that comes out to be 3.32. Okay, so the next thing in the problem that it asks you to compute is the covariance. And here's the formula for covariance. COV xy is equal to the sum of, it's called the sum of the cross products, the sum of the x deviations times, or the sum of the product of the x and y deviations. No squaring there. Divided by n minus 1. That part right there is y sub I minus y bar. So the sum of the x sub I minus x bars times y sub I minus y bar. So what I'm going to do is I'm going to create another column right over here, and it's going to be x sub I minus x bar times y sub I minus y bar. So I go to the deviations column. Everything's going to be in here for the x's and the deviation for the y's. And so I get the product of this minus 3 and this minus 3, and I get 9. What that's saying is that when x goes 3 units below its mean, y goes 3 units below its mean. So in the next column, I'm going to have 1 times 0 or 0. The next one, minus 4 minus 3 is 12. The next one, 2 times 1 is 2. And the last one, 4 times 5 is 20. And the sum of all those is 43. So the sum of these numbers right here, the sum of the cross products is 43, and that goes right down here, 43 divided by n minus 1, and that is equal to 10.75. Write that again here, 10.75. Okay, so now we have the means. Put those over here. The standard deviation of the x's, the standard deviation of the y's, and the covariance. Covariance, again, and the reason I calculate it out and show all those to you is it's how x and y move together relative to their means. It is a good measure of how the variables move together. One problem with it, though, is that the scale of the numbers can affect the size of it, and it's hard to compare one covariance to another if you have different variables or different groups or whatever. So to take care of that, we compute the correlation coefficient, R, and it's simply equal to the covariance of xy divided by the product of the two standard deviations. So in this case, the covariance is 10.75. 10.75 divided by the product of the two standard deviations, and we had one standard deviation here, just 3.39. Got a little bit of a rush there. That's 3.39 times the standard deviation for the y's, which is 3.32. And that all equals 0.955. I don't know why that's not writing. 0.955. That is the correlation coefficient, which is pretty close to 1. So if you drew the scatter plot in part A, just plotted the values of x and y, should have a pretty clear linear relationship. Almost all of the lines would fall exactly, all the points would fall exactly on the line. And that's the computation of correlation. That's the end of the lecture. I'm messing around here a little bit, but you're certainly welcome to turn off now.